Hello and welcome back to Math Class in Session. The cross product of two vectors. Vectors can be multiplied in two ways. One way, you get a scalar. That's called the dot product. The other way, you get a vector. That's called the cross product. Cross product definition. The cross product of two vectors is a vector of any magnitude that is perpendicular to the two vectors that are being crossed. The cross product of two vectors forms a right-handed system, and it can only exist in r cross r cross r. That's the only time that the cross product makes sense. Because what's happening is, given any two vectors, they define a plane, and the cross product is perpendicular to them both. So the cross product is a vector that sticks straight out of the plane, very much like a flagpole sticks straight up out of the ground. Now this right-hand system business, this is an illustration. If you took your right hand and put your right thumb along A cross B here, your fingers would extend along vector A, and as you curled them, they would go to vector B. And so we have A cross B is this vector. There's this plane defined by A and B, and the cross product sticks straight out like a flagpole. Now, if B cross A, if we wanted to find B cross A, we would again take our right hand and put our fingers along B, because B comes first, so our fingers go along where B is, and that would force our thumb to point straight down. And then we would curl our fingers and we would come over here to vector A. And so in this way, we have B cross A going the exact opposite direction as A cross B. Deriving the formula. So given a couple of vectors A and B, how can we find their cross product? A serious math student would be interested in where our formula comes from. And the only person I can conceive of who would be interested in a cross product would be a serious math student. So we'll go through the derivation of the formula. Given a vector A, A1, A2, A3, and vector B, B1, B2, B3, let V, X, Y, Z represent their cross product, A cross B. Now, by definition, V is perpendicular to them both. So those two dot products, A dot V and B dot V, must both be 0. So we'll set that up. A dot V, which is A dot V, perform the dot product and equate to 0. Do the same with vector B, B dot V, set it up, perform the dot product and equate to 0, generates a couple of equations. Now, we're going to perform the operation of elimination here on our two equations. You could eliminate X, or you could eliminate Y, or you could eliminate Z. I'll start by eliminating X. To do that, I have to make this term match this term. So equation 1 needs to be multiplied through by B1, and equation 2 needs to be multiplied through by A1. And then this term will be A1, B1X. And this one will be A1, B1X. So the first equation, everything times B1. Second equation, everything times A1. Draw a line, subtract, and the x's will eliminate. So it will be B1A2y minus A1B2y, and, well, I factored out the y, as I did the z. So it's boiled down to this. When we drag this term across the equal sign here, we have to multiply it by -1. And when we multiply it by -1, we multiply one of the two factors times -1. And when we multiply this factor times -1, the subtraction swaps places. So this becomes positive a1b3. This becomes negative b1a3. Now, in the textbooks, there's a popular way to do this so that I could make my solution in line with many textbooks. I've just multiplied both sides by -1. That's the purpose of swapping both of these now. So this negative a1b2 has become positive. This positive b1a2 has become negative. So I multiplied by -1 on both sides. Carrying that forward. Now, if I took the factor on the y and put it over here, and I took the factor on the z and put it under and over there, it would look like this. Now, I could use the same elimination process with x and y and eliminate z. And so I could get the same relationship happening between x and y. It would look like this. I didn't show the work on that part. And if you'll notice, this y is over a3b1 minus a1b3, just like this one is. So I can make this three-way equation. Because this expression equals this expression, as does this expression. So put them all together. Carrying that forward, because the cross product is a vector of any magnitude, we can choose our vector to be any multiple. Our x could be as long as it's the same multiple each time. So what we can assume is, since these three expressions are equal to each other, let's assign a value to those expressions of the number 1. It could be -1. But when they're equal to 1, then this side here is 1. And so x must match this expression. So our x must equal a2b3 minus a3b2. Similarly, if this is 1, the numerator has to match the denominator. And our rationale is that we're assigning a value of 1 to each of these expressions. We can do that because it's a vector of any magnitude. And when we do that, we get a formula for the cross product. And there it is. The derivation. Now, in practice, how do we find a cross product? Well, we could memorize this formula. Myself, I find it cumbersome with all the subscripts. But that's just me. If you like those subscripts and you can memorize that formula, I invite you to go ahead and do that. However, if you don't like all the subscripts, there's this way too. On the left of these crosses, make 3 big crosses. Call them X, Y, Z. And on the left, reference your vector A and state middle, last, first, middle. So that's middle, last, first, middle. Just get that saying going in your head. This is middle, last, first, middle, referencing these 3. Similarly for B, over on the right-hand side here, we'll reference the middle number, the last, first, middle. Middle, last, first, middle. And then we get X being the difference between the down products subtract the up products. So A2B3 minus A3B2. Similarly for Y and Z. Z, for example, would be A1B2 minus A2B1. The down products minus the up products. There's our formula, and there's a way to perhaps use it. Properties of this cross product? Well, it's not commutative. A cross B is the negative of B cross A. However, it is distributive, just the way you think it would be. The cross product of a sum is the sum of 2 cross products. And a scalar multiplication, so a multiple of a cross product, well, we could take that k value multiple and first multiply it by either one of the two vectors and then cross them. So we could cross first and then multiply by a scalar, or multiply the scalar by either and then cross. So that's the associative property. Here's an example. Let's do this example. Given a couple of vectors, calculate their cross product. So there's u, there's v, find u cross v. V cross u will simply be the negative of that. So we set up these crosses. They look like that, x, y, z. That's going to be the cross product. And at these intersections, there's going to be middle, last, first, middle. So it'll be -4, 2, 5, -4. Similarly, on the right side, we'll take middle, last, first, middle. So it'll be -3, 5, -8, -3. And so to find the actual cross product now, it will be the down product subtract the up products. So our cross product will be -20 subtract negative, so +6. That's where we get -20 +6. And then -16 -25. The down product minus the up product, so -15 -32. Work them out and we have the cross product. And v cross u is simply the negative. Change the signs on each. And we found a vector that's perpendicular to them both. We can check that it's perpendicular to them both. How? By taking our cross product and dotting it with each and seeing if we get 0. Well, I took it and I dotted it with the first one, which was 5 - 4, 2. And what do we get? -70 plus 164 minus 94, and that is 0. Similarly with the other one, -8, -3, 5, just multiply it out. 112 plus 123 minus 235. Minus 235. Work that out, and of course, yes, you get 0. So we found a vector perpendicular to them both. From a recent video, there was a question came up. Find a vector perpendicular to both of those vectors, 2, -3, 7, and -1, -1, 4. And how we did it was, on that video, we wanted to find this vector perpendicular to them both, gave it a name. We dotted them each to 0. So we came at it from the other direction. We started with the check. Since u is perpendicular to the given vectors, u dots to 0 with each of them. And this generated equations, because this dot product means 2x minus 3y plus 7z equals 0. And we have 2 equations, but we've got, darn it, 3 unknowns. Now what's going to start to happen in math class is we're going to start to get different numbers of equations and different numbers of variables. Now in this case, we had too many darn variables, and so one of those variables has to play the role of a parameter. So when you've got lots of variables, one of them becomes a parameter. We did this, and we solved, and we worked on it, and we eliminated, and we got y in terms of z, and we did some more work, and we got x in terms of z, and so since they're both in terms of z, z became our parameter, and we gave it a name, we called it t, and we had this. Our vector u perpendicular to them both is that, t, 3t, t, which we could factor out the t, and we would have a multiple of 1, 3, 1, any multiple. That's how we did it before. But we've got a new way now. We could just cross the vectors. Middle, last, first, middle, remember? But I started here. Middle, last, first, middle. And over here, we'll do middle, last, first, middle. And work out this cross product, and we're going to have -7 plus 12. We're going to have 8 plus 7, and we'll have 3 plus 2. Work these out, we get 5, 15, 5. So we could just cross the vectors and we get a vector perpendicular to them both, but the other way, with the use of a parameter, we had any multiple of 1, 3, 1. So that's a couple of ways to find vectors perpendicular to two vectors which are defining a plane. Let's remember, if you've got an extra variable, you can make it a parameter. From a previous video, we did something else. We determined if given three vectors, we determine if the given three vectors are coplanar. So we were given three vectors, and the question was, are these vectors coplanar? And our solution was to express one as a linear combination of the other two. So we said that this vector v1, 2 minus 3, 5, was a linear combination of the other two. And when we multiply these out, we had three equations in two unknowns. So in this case, we don't have an extra variable for a parameter. What we have is an extra equation. And when we have an extra equation, we care very much about whether the system is consistent. So we took any two of the equations and solved them, came up with values that work, and tested it in the third. And it worked. And we concluded that the vectors were coplanar because we could express one as a linear combination of the other two. Because we were successful in expressing one as a linear combination of the other two. Now that we know about cross products, there is a different way to determine if three vectors are coplanar. So we could take those same three vectors, pick any two of them, say v1 and v2, and find their cross product. So I'll cross v1 and v2, and I'll get this. Now please don't take my word for it. Cross them yourself and get that. Take this result and dot it with the third vector. So it will be v3 dotted with the cross product. So v3 dotted with the cross product, performing a dot product, and we get 0. And it's a fact that if three vectors are coplanar, when you take two and cross them and dot it with the third, you get 0. Of course, we could, what's the other method again? Express one as a linear combination of the other two, get three equations, and then find out if those three equations are consistent by solving two of them and then checking with the third. In summary, three vectors are coplanar if and only if the dot product of any one with the cross product of the other two is 0. It's called this triple scalar product, and it looks like this. This symbol means if and only if, and it means the left side implies the right side, and the right side implies the left side of this symbol. So the dot product with the cross, so cross and dot, get 0, implies the three vectors are coplanar.